Hello and welcome to lecture 21 of Math 2R03. In today's lecture, we're going to be looking at generalized eigenvectors, and then we'll be also introducing nilpotent operators. So basically, we're going to be finishing up section 8.A in today's lecture. And in today's lecture, I'll give you a little bit of a warning here. We're going to get into kind of the weeds. We're going to look into a lot of the details of kind of two main results dealing with generalized eigenvectors and nilpotent operators. So to start for today's lecture, just let me kind of do a quick recap of where we were last time. Remember, we said that if we take an operator, and if we take n equaling to the dimension of our vector space, and if we know if lambda is an eigenvalue, that the generalized eigenspace of lambda is the set of all vectors that are in the null space of the operator t minus lambda to the times I raised to the power of n. And we call a vector in this set a generalized eigenvector. So an eigenvector is the case where n is equal to 1. It's the null space of this particular operator. But we're allowing now the powers of this operator, and any vector that lives in this set here is called a generalized eigenvector. Now, one of the important results that we know about eigenvectors, not just generalized eigenvectors, but just specifically for eigenvectors, is that if an eigenvector, if you look at distinct eigenvalues and you look at their corresponding eigenvectors, then they're linearly independent. But it turns out that the statement is still true if we talk about generalized eigenvectors. So if you take an operator and if you take distinct eigenvalues of that operator, and if V1 is a generalized eigenvector lambda 1, V2 is a generalized eigenvector lambda 2, and so on, then those vectors V1 through Vm are linearly independent. Now you may want to just pause and go look at this proof that we did back in chapter 5 when we scratched out generalized, right? We just looked at regular eigenvectors, and the proof's not too hard. Now to prove it for the more generalized case, it takes a little bit more work, but I'll try to walk you through the proofs, and hopefully this will complement what's in the textbook. And the proof is by kind of contradiction. Well, not necessarily contradiction, but what we're trying to do is show that suppose that we have a linear combination of V1 to Vm, and it equals to 0. Our goal is to show that each of these coefficients are 0, because that would imply that the vectors are linearly independent. So what we're going to do is we're going to start off by letting k be the largest integer such that, okay, and let me just to, before I go any further, let me preface this by saying we're first going to focus on V1 and we're going to show that A1 is 0. And then this proof that I'm going to give will actually then be allowed to show that any of the other coefficients are 0. So let k be the largest integer such that t minus lambda 1 times I to the k times v does not equal 0. Okay, so and I want to point out here is that the k can be 0. K can be 0. So the 0 case would be that you're taking a vector that's the k equals 0 is just saying that this is the identity operator, so I times v not equal to 0 means that the vector is 0. And if k is if k is 0, that means that if I take this power 1, it's just saying that v is just a regular eigenvector. Okay, so but oh, and I should put the 1 there, that's the key point. So because v1 is a generalized eigenvector, some power of this operator will put it to 0. So we're looking at the smallest power k before you become 0. And so what we want to do is, this is a non-zero vector. So we're going to set w to be this non-zero vector. And what can we say about that? Well, then if I apply the operator t minus lambda 1 I to w, okay, one more time, this is the same thing as taking t minus lambda 1 I times t minus lambda 1 I to the k times v1. And this becomes, just the same as t minus lambda 1 I raised to the power of k plus 1 times v1, and this has to be 0, right? Because we took k to be the largest exponent we can put here before it's non-zero. So if I take k plus 1, it goes to 0. And what this means is that if we look at the beginning part, this means that t evaluated at w is the same thing as lambda 1 times w. Okay, so that's kind of what we're getting out of here in this particular computation. Okay, so let's put that to the side for a second. So we know that t evaluated at w is this value, and w is this particular vector. Okay, carrying on. Now we're going to look at any number lambda, and we're going to look at what happens when we take t minus lambda I evaluated at w as well. Well, when we do that, we know that we have, this is tw minus lambda iw, and tw, we just saw on the previous page, is lambda 1 w, and then on this side I get lambda w, so I get lambda 1 minus lambda times the vector w. Okay, so if I now take the operator t minus lambda I to the n, okay, so I raise this operator to the power of n, that's the same thing as doing lambda 1 minus lambda raised to the power of n times w, and this is true for all lambda in f, and n being equal to the dimension of v. Okay, so we've now said something special about the operator t minus lambda I to the n corresponding to the vector w, where w is this particular vector here. Okay, so the next stage is we now cook up an operator. T minus lambda 1 I raised to the power of k. The k is coming from this expression right here. And then all the other operators we're raising to the power of n. So we're using the other eigenvalues to make operators. So t minus lambda 2I raised to the n, and so on. And we're applying this to star. So star was our initial expression. Okay, so using the properties of linear operators, okay, what we're getting here would be, we get the expression that 0 is a1 times t minus lambda 1 raised to the power of k, and then t minus lambda 2I to the n, all the way to t minus lambda I, t minus lambda m times I raised to the power of n, evaluated at v1, plus a2 t minus lambda 1 I k t minus lambda 2 I raised to the power of n, t minus lambda m times I times n evaluated at v2, and we carry on all the way down to the end. Okay, so we would, the last term here is going to be am t minus lambda 1 I k t minus lambda 2 I n t minus lambda m I n v m. Okay, so we're just using the fact that this is a linear operator and we're applying it to this expression. So it just means we're taking a1 times whatever this operator does to v1 and so on. Okay, so one of the properties that we have are these operators commute because they're coming from polynomials. Okay, so the operators commute. So if I look at, let's say if I look at the second row right here, I look at the second row right here, I can take this operator involving the lambda 2 and I can push it all the way to the end. Okay, I can push it all the way to the end. So I can take t minus lambda 2I to the end, v2. But v2 is a generalized eigenvector. So that means that when I plug it into this operator, I get 0. Okay, and that's actually true for each of the vectors v2, v3, all the way up to vn. If I take vj and I plug it into this operator, I have to get 0 since vj is a generalized eigenvector of lambda j. Okay, so what that means is we can kind of push the correct term to the end beside the generalized eigenvector, and then it just kills everything. So everything kind of disappears involving a2 to am. So all terms with v2 to vm are killed, and what we're left over with is just the first term. Okay, so we're left with just the first term, and I'll put that over here. We're left with this particular term right here. But now we can, again, move these operators around in any order that we want, right? So I can move it around so that I'm going to put the first one, I'm going to put it at the end. So I have t minus lambda 2I to the n, and then I have t minus lambda mi raised to the power, oh, I forgot an I up here, I to the n, and then t minus lambda 1 I raised to the power of k times v1. And this part here, remember, is equal to w. That's how we defined that particular value. So we have a1 t minus lambda 2 I n t minus lambda m I n w. But now we can use the fact that we know that we have this identity. Whenever you plug w into one of these expressions, you get lambda 1 minus whatever the lambda is. So everything here will now collapse to the expression that we have, which will be a1 lambda 1 minus lambda 2 raised to the power of n, and then lambda 1 minus lambda 3 raised to the power of n, all the way to lambda 1 minus lambda n raised to the power of n w. Okay. Now all of our eigenvalues are distinct. Okay, so just to kind of recap, what we have here is now the zero vector is a1 times these constants times the vector w. And w isn't the zero vector. And what we know is each of the eigenvalues are distinct. So each of these terms are distinct. So this isn't a zero vector. These are not the zero number for each I. So we have to have that a1 is equal to 0. Okay. So then we've shown that a1 is 0, and now we just have to go back and do the same argument to show that a2 and a3 all the way up to am is equal to 0. So this shows that the eigenvectors are linearly independent, right? So v1 up to vn are linearly independent. So hopefully this kind of proof here, detailed proof, kind of expands upon what they did in the textbook and helps you understand this proof in a little bit more detail. So we'll pause here and move to a different topic in the second part.